Okay, so it's 5 past the hour, so I think it is time to start the seminar today. Our presenter for the iBEST seminar today is Dr. Scott Tsai. Dr. Tsai is an associate professor in the Department of Mechanical and Industrial Engineering at Ryerson University and an affiliate scientist at the Li Ka-shing Knowledge Institute of St. Michael's Hospital. He obtained his Bachelor of Science in Mechanical Engineering at the University of Toronto, his SM, which is the weird Harvard way of calling MSc, at Harvard, and his PhD also in engineering sciences at Harvard University. He's the theme lead for the Biomedical Delivery Systems theme of the iBEST, and he directs the Laboratory of Fields, Flows, and Interfaces, or LOFI, if I pronounce it right. Yeah, LOFI. So starting in January 2020, also Dr. Scott Tsai will be the interim graduate program director of the Biomedical Engineering Graduate Program, and he's the recipient of several awards, and I'll just highlight a few. The Fulbright Visiting Research Chair Award in 2018, the Ontario Early Career Research Award, or the ERA, in 2016, the Canadian Society of Mechanical Engineering's I.W. Smith Award in 2015, and various Ryerson Awards that talk about his ability to teach and his research. So Dr. Tsai, do you want to talk a little bit about shrinking things?
All right, thank you, Michael, for that wonderful introduction, and thank you for being here, everyone. So today I want to tell you about microbubbles and nanobubbles, and specifically how we can use microfluidic technology to both generate these bubbles and also to subsequently shrink them down to the sizes that we want for different biomedical applications. So the really nice part about working with bubbles is that it's very intuitive. So I think all of us, or if not most of us, if not all of us, have played with bubbles when we were children, and some of us, even as adults, still play with them. And so because we have so much experience with bubbles, we tend to have very good intuition about bubbles. This is my daughter, my younger daughter, Chloe, and this is her when we were at Disneyland in California earlier this year, and she's playing with bubbles. And they have these really amazing toys now. So this is like a bubble, I guess it's like a bubble wand, and so it's able to generate at a very high throughput of roughly 20 to 30 bubbles per second. So this is really amazing toys now. So when Chloe was born, and some of my colleagues know about this, when Chloe was born, she was born with this congenital heart defect called atrial septal defect. So this is a schematic about ASD, or atrial septal defect. Primarily what happens when somebody has ASD is that when they're born, there's a tissue here called the septum that's supposed to seal so that it blocks any communication between the left and the right atria. So in Chloe's case, and everybody else who's born with ASD, this septum does not close, and therefore blood is able to flow in between these two chambers. The problem with that is that when this happens, you have oxygenated blood from one of the atria flowing into into the other chamber that has deoxygenated blood, which means that the blood that's supposed to be oxygenated going into circulation ends up not having the optimal amount of oxygen in it, because some of that oxygen is lost to the other chamber. So in Chloe's case, thankfully, when she was 5 months old, she had an open heart surgery at Sick Kids Hospital, and they were able to repair that hole in her heart. And so as you can see, she's very active now, and she's doing really, really well. So the reason why I'm talking about this is because bubbles are also related. So it turns out a very common way that's used to diagnose ASD is with what's called bubble contrast echocardiogram. And so I'll try to pull up this video here to show you how that works. So in an echo study, or an a bubble echocardiogram, what the doctors will do is first they'll take a Luer lock system like this, and So the outlet of this lower lock system will go to the patient's IV. And then there's two inlets to this lower lock system. And one of them, they'll insert a syringe that has saline and some stabilizing agents inside. The other one will have a little bit of air inside. And so what happens is they will connect the two syringes first to the lower lock system with the valve closed. And then they will generate the bubbles. And the way they generate the bubbles is they push the liquid and the gas through the lower lock system as such, so that there's a lot of agitation involved and bubbles are then generated. And at some point, they will then connect the outlet to the patient's IV. So here, so they'll connect the patient's IV, and then they'll open that valve and inject the bubbles into the patient's blood. And so in the ultrasound image of the heart, you'll then be able to see the bubbles appear in one of the chambers of the heart. In this case, the patient's septum is fine, and so you don't see bubbles going to the other side or the other chamber. But for somebody who has ASD, you would see the bubbles migrating from one chamber to the other. Okay, so what are these bubbles? So it turns out bubbles are used not just in bubble echocardiogram, but also in other ultrasound imaging applications as well. And typically, these bubbles are made with a gas core and some kind of a stabilizing shell, and it's surrounded by liquid. Okay, so the gas core oftentimes is made out of air or nitrogen, or sometimes if they want the bubbles to stay in the bloodstream for a longer period of time, they will use a larger molecule gas, such as perfluorocarbon. And then that bubble is then stabilized with a shell, and the shell is often made with lipids or polymers and other amphiphilic molecules. And the shell enables the bubble to not coalesce with neighboring bubbles. So in ultrasound imaging, with bubbles, the ideal size range is between 1 to 3 microns in diameter for the bubbles. The reason why bubbles work to enhance ultrasound imaging signals is because bubbles are compressible. So gases generally are compressible. The blood and tissue are generally considered incompressible material. And so when a bubble, when there's an ultrasound pulse coming towards a bubble, the bubble will compress and then expand, and that expansion then causes a strong ultrasound signal. And so there are lots of applications of these bubbles in biomedicine. Right now, where it's commonly used is in echocardiograms and also in the diagnosis of various cancers. Some of these are FDA approved. So for example, this product here called Definity has FDA approval for clinical use. There's also quite a sizable market globally for these contrast agents, about $800 million per year. And in the scientific literature, there's also a lot of discussions about future applications of microbubbles in medicine, and that includes functionalizing the surface of the bubbles so that they can be targeted towards specific regions of the body. So I just want you to note about, remember about how in the bubble echocardiogram, how they made the bubbles. So they just pushed and pulled the syringes back and forth to agitate the system, and that causes the bubbles to form. And that's generally how these commercial bubbles are formed. And if you look at Definity, this commercially available product, and you look at its instructions, it's similar. So it says to activate Definity, you do so by shaking the vial for 45 seconds using this machine that they have called the vial mix. Because that means in all of these products, the way that you make the bubbles is just by vigorous agitation. Okay? And that means the bubbles are formed in a kind of a chaotic manner without too much control. And so what this means is that the bubble distribution in such a system can be pretty broad. And so there's a study of another commercially available product called SonoView. And this published study shows that the bubble, so the y-axis here is the gas volume, and The x-axis here is the diameter. So the gas volume is the total gas volume for that specific, that is attributed to that specific size of bubbles. And as you can see, a large amount of the bubbles, so here 87%, are above 3 microns in size. And the amount of bubbles by volume that's within the desired size range of 1 to 3 microns is actually fairly small. Okay? And so that means most of the bubbles that are injected are not in the size range that you want them to be. They're higher than that size range. The consequence of this is that the ultrasound imaging is not optimal. Okay, so in this published paper, they state, so in this paper, what the authors have done is they studied 2 groups of bubbles. So one group of bubbles comes from the commercially available products that they use directly in their ultrasound imaging experiments. In the second group, they use a microfluidic method to sort out bubbles so that they isolate just the bubbles of their desired size and compare the imaging results with those bubbles versus kind of the more randomly generated bubbles. And they find that sorted monodispersed agents for bubbles had up to a 2 orders of magnitude increase in sensitivity. So that's 100 times more sensitive than these polydispersed random sized bubbles. Okay, so that's really important. And it means that there's a lot of room for us to work and to try to optimize the performance of these bubbles. So to summarize kind of the challenge and the approach, the challenge is that commercially available bubbles and these FDA-approved bubbles that are used clinically tend to be polydispersed. That means their size range is quite large, and so the imaging is not optimized. And the approach that we want to take is with microfluidics, we can generate monodispersed bubbles, so bubbles that are almost exactly the same size, and we can tune the size of these bubbles to enhance the ultrasound contrast. So this is one microfluidic experiment that we did in the lab, and you can see here we can generate bubbles, and all of the bubbles look like they're roughly, basically the same size. So that's what I mean by monodispersity. And the reason why microfluidics is able to do this is because we have very precise control of both the gas pressure and also the liquid phase flow rate. And so bubbles are generated one at a time, but at a very high throughput and preserve their monodispersity. So we're actually not the first to realize that we can do this with microfluidics. There's been literature for 10 years now where people have been trying to make bubbles with microfluidics. The challenge is that we want to make bubbles that are within the size range of 1 to 3 microns. But if you talk to any microfabrication expert, they'll tell you that with conventional microfluidics fabrication techniques, the smallest feature size that you can confidently achieve is about 10 microns. And that means that if this orifice has a width of about 10 microns, the smallest bubble size you're going to get typically is about 10 microns. And it's very difficult to make microfluidic bubbles below that size. Okay. So what do we do? So we came up first with this approach of making bubbles that are bigger, because with microfluidics, it's easier to make slightly bigger bubbles that are on the order of tens of microns in size. And then what we want to do is apply a vacuum to shrink the bubbles down to the sizes that we want. So that's the main idea. So we would generate the bubbles at the inlet in a kind of a typical fashion. And then downstream of that inlet, we would build these interdigitated channels that have vacuum, that has vacuum inside to suck air out of the liquid phase, which then removes air out of the bubble to make them smaller. And you can see experimentally, we generate large bubbles, but downstream, by using this vacuum pressure approach, we can make bubbles much smaller. And this work was done, the experimental work was done by a former PhD student Vaskar, also a former postdoc Biani, and also a current student Jennifer. And the ultrasound imaging aspects of the work were done in collaboration with Michael and also Rafi Kershafian, both from Ryerson University. The basic idea is this. So we have a bubble, and the core is made out of something like air. The shell is made of some kind of amphiphilic molecule. And if we apply vacuum pressure, then we remove the amount of air that's originally in the liquid phase. So the liquid phase becomes not saturated anymore with air. That then allows it to have capacity to receive more air from the bubble. And so then the air molecules come out of the bubble and the bubble shrinks. That's the basic idea. Experimentally, again, you can see this in the video. The bubbles are generated at a pretty large size and very monodisperse. And downstream, because they're exposed to the vacuum, they shrink and they shrink and they shrink until they get very, very small. Okay? And the neat thing about this approach is that with the vacuum pressure that we apply, we can get different bubble sizes. So here, the y-axis is a normalized bubble volume, and x-axis here is the pressure of the vacuum. And you can see that there's a monotonic decrease in the bubble size with decreasing pressure from the vacuum channel. Right? So the stronger the vacuum we apply, the smaller the final size of the bubbles. And that makes sense. That means we can tune the bubble size. Say we want 1 micron, we can make those. If we want 3 microns, we can also make those. We also look at the dynamics of how these bubbles shrink. So here, the y-axis is also, again, the normalized instantaneous bubble volume. And the x-axis is the position of the bubble along the length of the channel. And we see that bubbles decrease in their size along the length of the channel, and they decrease the fastest when you have the strongest vacuum pressure. So that's pretty clear. We next also try to mathematically model how the bubbles will shrink with respect to time. And this work was done by my student with Michael Ali Solari at Ryerson, and also a collaborator, mathematician Ian Griffiths at Oxford. So we developed a full numerical model that you can solve, you can get an estimated solution for with numerical modeling. And then we turn that around and turn it into an exact full analytical model. And then Ian was able to help us then to reduce that into a simplified, approximate analytical model that looks like this. And this works in the limit that the bubble elasticity and surface tension become negligible. So that means surface tension becomes, the effect of surface tension on bubble size becomes very weak. And here we see that this approximate solution actually collapses very well onto the full solution. Okay? The data overlaps really well. What that suggests, and it'll turn out to be really important, is that these other parameters, like surface tension and elasticity, are not very important in determining the size, the final size of the bubbles. And also importantly, if you look at this mathematical expression, you'll see that the diffusion coefficient, which is indicated by kg here, appears to the power 1. So kg to the power 1 here, kg squared, and then there's a square root over that, so it's also to the power 1. But the other factors are all lower in power. So for example, the gas saturation level in the liquid is to the power of 1/2. The vacuum pressure also is not as strong, it's also to the power of 1/2. This hints to us, although I think we didn't realize it at the time, that the diffusion coefficient of the gas phase in the liquid is the most important parameter that decides whether the bubbles will shrink or not, and by how much they will shrink. Okay, so remember that it's the diffusion coefficient of the gas in the liquid that is the most important. And so this is all great. So we published a paper in Soft Matter. It's called Honey, I Shrunk the Bubbles. And so everybody loved it because it's a funny play on a movie. We also then worked on the mathematical modeling. We also published that in Soft Matter. And this ended up being featured as a cover article of Soft Matter. We were also interviewed by a British magazine called Chemistry World. And most importantly, we made it on the cover of Ryerson Today. Yeah, so this is so great, right? So researchers make waves in the ultrasound world. So it's really great. And so we were thinking to ourselves, what's the next thing we should do? Well, we should bring this closer to clinical application, right? And so what we should do then is to take these clinically approved gases and put them into our microfluidic device, shrink them to the size we want, and then put them into a mouse model to see what happens. So what happened? So we tried this. Excuse me. So Ali, who's our PhD student, was the one that did this experiment with perfluorocarbon gas, which is a large molecule gas that's FDA approved as an ultrasound contrast agent gas for ultrasound imaging experiments. So he put the gas in our microfluidic device to make bubbles. And then I remember really clearly that it was one Friday afternoon when we were having a research meeting in Michael's office at Ryerson. And it was myself, Michael, Ali, and Bhaskar who were in that meeting, right? And this is an approximation of what happened. Okay, so Ali is presenting us the data from his experiments, and he says something to the likes of, so the bubbles that are made with clinically used gas don't actually shrink. Even at kind of maximum pressure, that vacuum pressure that we can exert, they don't shrink. And that's when I think all of us kind of had this really big realization that something is really bad here. This is Michael, Bhaskar, and me, and we're just like, oh no! And it's just really, really bad. So what's the reason why these large molecule gases don't shrink? Well, in our original Honey, I Shrunk the Bubbles paper, we had air as the gas phase. And so air, it turns out, dissolves really well into water. And I think most people know that, but for some reason, we didn't think about this. And so when you apply vacuum pressure, it shrinks. But large molecule gases like perfluorocarbon have a very low diffusion coefficient in water. And so what happens is, even in the presence of vacuum pressure, the bubbles don't shrink because the large molecule gases don't want to go into water. Okay, and so so what do we do? So it turns out we actually kind of knew this. If you go back to our mathematical model, which was published like a year earlier, we recognize that the fact that our approximated model, which only takes into account diffusion coefficient and pressure and gas saturation and nothing else, the fact that that model collapses so well onto the full analytical model that takes everything into account, that suggested to us that the most important parameter is the gas diffusion coefficient. And in this case, the gas diffusion coefficient between air and perfluorocarbon is very different. And so the results would be very different as well. And so now it's very clear to us why that large molecule gas did not shrink in our system. And so what should we do then? We kind of made this promise already that this would be the microfluidic approach to shrink bubbles down to the sizes that you would want for ultrasound imaging. But it doesn't actually work for the gases that people are using in the clinic. And so we came up with the sequel to Honey, I Shrunk the Bubbles. And usually, so I haven't actually seen any of the sequel. I only saw the original movie, but usually the sequel doesn't do as well as the original. But in our case, I think many will agree with me that the sequel is much better than the original. What's the sequel? So this is the idea that we came up with. So instead of having just large molecule gases like perfluorocarbon or just air, we would mix the two gases together. Okay? And what happens if you mix the two gases together? Well, if you mix the two gases together, then in solution, the small molecule gases would then dissolve into the aqueous solution. The large molecule gases will not, right? And so the bubble will shrink, but it won't disappear. But rather the final size of the bubbles will be dictated by the number of large molecule gases, gas molecules that are in the bubble in the original setting, right? So then you can get very good control of the final bubble size, right? And so this is the idea here that we ended up pursuing. So this work was led by my postdoc, Jiang Su, and working with Ali and also an undergraduate student, Liam, in our lab. And so the microfluidic schematic is very similar to what we had previously. We have a gas phase flowing into the microfluidic channel. And next to that gas phase, we flow a lipid solution that's in the aqueous phase. And at the junction here, microbubbles are formed. So relatively large microbubbles are formed. And then downstream, what will happen is the bubbles will shrink because the small molecule gas, here we use nitrogen, will dissolve into the aqueous phase, whereas perfluorocarbon, which is a large molecule gas, will stay inside the bubble. And so once the bubble reaches this steady state size, then it will it will no longer shrink. And here, the students collect the different bubble samples with different size bubbles, and you can see that they have different shades of color depending on the bubble size that we get. Okay, so here's an experimental video of bubbles being generated. So here's at the orifice, the bubbles are being made. These are smaller bubbles to begin with, but downstream, you can see we have lots of bubbles, and they will shrink as they go further and further downstream. And yeah, you can see they get smaller and smaller until they reach a steady state size and they don't shrink anymore. Okay, and so this is the basic idea. At the orifice is big, and then, by the way, these numbers indicate the number of turns that we have in our serpentine channel. So the higher the number, the further downstream the channel is. And so you can see very, very downstream in the microfluidic channel, the bubbles are very small. And also importantly, the bubbles are very monodisperse. And that's because the initial bubble is very monodispersed, because we can make it easily in microfluidics. Every bubble has the same gas mixture ratio, right? So the amount of large molecule gases in every bubble will be the same. And therefore, the final bubble size will also be the same. So it's a very elegant approach. So we test this with different mixture ratios of perfluorocarbon and nitrogen. And you know, we can see very clearly that if there's no large molecule gas, if there's no perfluorocarbon, then what happens is the bubble shrinks immediately. So within like 10 seconds, it shrinks and it goes to a very small size. On the other end of the spectrum, if you have completely large molecule gas, then the bubbles just shrink slightly because even though the diffusion coefficient is very low, it's not a zero diffusion coefficient. So it'll shrink slightly and then it reaches a steady state. Okay, and we can make everything else in between as well by changing this gas mixture ratio. And so we can get different final size of the bubble. So here the y-axis is the final diameter of the bubble. The x-axis is the percentage of large molecule gas we have in the gas mixture. And you can see if we have a small amount of large molecule gas, then we can get bubbles that are very small. Here, they're even under 1 micron in size. And so we can clearly make those 1 to 3 micron bubbles now with a good degree of monodispersity. Another experimental image here showing the different bubble sizes we can achieve. Here, A1, A2, and A3 refer to 3 different initial size bubbles. So the other way we can change the final size of the bubbles is by changing how big they are when we make the bubbles. Right? So if we make bigger bubbles, then they'll shrink down to bigger bubbles. If we make smaller bubbles, they will shrink down to smaller bubbles. And here again, we can see the dynamics of how they shrink with respect to time. And interestingly, so before we tried all of this, we didn't know that this was possible, but now, because this approach is so controllable, we can actually make nano-size bubbles. So now this is sub-micron bubbles with a good degree of monodispersity. So you can see here, for example, A3 is about 100 nanometers in size, and the error bar, which is 1 standard deviation, is fairly small. Okay, so this is really interesting because at that time, sorry, let me backtrack a little bit. So here, going back to an earlier slide, we can definitely make 1 to 3 micron bubbles now, 1 to 3 micron size microbubbles now with a good degree of monodispersity. But what's more interesting is that at about this time, Michael was collaborating with a scientist, Dr. Agatha Exner from Case Western Reserve in the US, and they were using her method to make nanobubbles. But not with microfluidics, with kind of a bulk agitation style manufacturing method. And Dr. Exner is an expert at developing these shell materials using lipids and other formulations. And so she was able to develop a shell material that upon agitation, the bubble size that you end up with ends up being in hundreds of nanometers. And so that was very interesting. And they studied this in tissue as well. And they find that these nanobubbles versus microbubbles, the difference is that nanobubbles then can exhibit a better amount of ultrasound contrast. And also very interestingly, because these bubbles are so small, they can now extravasate into the tissue rather than staying inside the bloodstream. And also, if we look back at the historical literature, we find that there's a lot of interest in nanobubbles, even from a fundamental standpoint. There are questions, even just a decade or two ago, about whether or not nanobubbles can even exist. And the reason for that is there's something called Laplace pressure in fluid mechanics that tells you that the smaller a bubble is, the larger the pressure will be inside. And so if you get down to the nanoscale, theoretically, the pressure inside the bubble should be enormous, and that should push all the gas molecules into the liquid, collapsing the bubble. And because it's a vicious cycle, so as it pushes the gas molecules into the liquid, the bubble gets smaller, the Laplace pressure increases again, and more gas gets pushed into the liquid. And so theoretically, nanobubbles should just collapse. Okay, and so there was always questions about whether nanobubbles can exist. And then people experimentally found that they could measure nanobubbles. And then recently, people started thinking about applications of nanobubbles. So fundamentally, this is also a very interesting area of research on making nanobubbles. So going back to our experiments, then we realized that we had a tool that can enable us to make pretty monodispersed nanobubbles. And so these are distribution curves for the nanobubbles that we're able to make. And so again, A1, A2, A3 refer to 3 different initial size bubbles, and we can shrink all 3 down to a different final size. And again, we can get them to be about 100 microns, 120 microns, 150 microns, and with pretty narrow bands of distribution. So compared to what Dr. Exner and this kind of agitation approach is able to make for nanobubbles, the distribution curve is much broader in that kind of experiment. And if you look at it under transmission electron microscopy, you also see that microbubbles made using microfluidics, using our approach, all appear to be about the same size. Whereas, nanobubbles. And nanobubbles that are made using kind of the bulk agitation type approach tend to be more monodispersed, as you would expect. Okay, so now we can make these nanobubbles really monodispersed, right? So, and you can see, going back to Dr. Exner's experiments, these kind of really interesting images come from polydispersed or bulk agitation made nanobubbles. So imagine now then, what if we had monodispersed nanobubbles, bubbles that are all basically the same size, and that you had the ability to tune their specific size. We again went back to Michael's lab, and this is work done by Yan from Michael's group. So she was able to put these nanobubbles of ours along with microbubbles into these phantom vessels and image them with ultrasound. And you can see in a blank solution, clearly there's nothing happening. And when you have bulk nanobubbles, so these are bubbles made by agitation, you can see, at least in the nonlinear image, nonlinear mode image, that there's a greater spread of intensities throughout the phantom. Whereas with these monodispersed microfluidically made nanobubbles, the intensity is pretty uniform inside the phantom. And because we're at the iBEST, right? So we also went to Dr. Darren Yuan, who is interested in working with bubbles in kidney. And so he was able to, his group with Xiaolin He was able to do these in vivo experiments on live mouse. And so they injected our nanobubbles into the tail vein of the mouse, and we were able to image them and see what happens. So here, this is a video of the kidney of the live mouse. And you can see the first injection here is are microfluidically made nanobubbles. So these are monodispersed nanobubbles. And you can see both in the B mode image and also in the nonlinear mode image, you can see when the bubbles come in that they go pretty much everywhere in the kidney, and you can see the contrast very clearly. And so here, then the wash away. And then, so when we inject these bulk made nanobubbles, so these are agitation-based nanobubbles, at the same concentration as our microfluidically made nanobubbles, you see very little contrast in the nonlinear mode. Okay, so here they're already injected. And so what you can do then is you can, so here, if you inject a bulk made nanobubble solution that's 1,000 times greater in concentration, then you can see something. in the mouse kidney. But you also see some shadowing here due to what we think is attenuation of the ultrasound due to just an overabundance of nanobubbles here. And because the transducer is coming from the top, and so the bottom of the kidney here, the signals tend to be attenuated. So this is what we observe here. Microfluidically made nanobubbles at lower concentrations are able to produce very good contrast kidney. Bulk made by agitation made nanobubbles at the same concentrations do not exhibit this kind of contrast. But if you increase the concentration of these bulk made nanobubbles by 3 orders of magnitude, yes, you can get good contrast, but we also find there's a shadow effect, possibly due to attenuation. So this is the story I wanted to share with you today about micro and nanobubbles. The takeaways are I think, that with microfluidics, we are able to make monodisperse both micro scale and nanobubbles. So microbubbles in the ideal size range for ultrasound imaging, that's very easily accomplished now using microfluidics. But perhaps more interestingly, we can now scale down the bubble size to the nanoscale. And that opens up different possibilities for example, imaging the extravasation of the nanobubbles into tissue. And when that happens, when that doesn't happen, how that is related to disease, for example. And another note is that the monodispersed nanobubbles made using microfluidics, they exhibit more uniform ultrasound contrast compared to nanobubbles that are made using other methods. And importantly, to the best of our knowledge, this is the first demonstration of monodispersed nanobubbles made using any method. And so this is really an important contribution. And before I end, I just want to acknowledge a bunch of people. And you know, this is really, I think, an artifact of us being at an institute like iBEST. You know, we can, on the 7th floor, we can make the nanobubbles, design the microfluidic systems in our lab, in our clean room. And we can make all the nanobubbles, walk over to Michael's lab, which is across the hall, and they can do the phantom experiments there. And then we can take the bubbles, walk over to Darren Yuan's group, and they can do the animal model experiments there. And I just can't imagine, you know, anywhere else where this is something like this is really possible. And so I want to acknowledge, obviously, Michael Kolios and his group, Darren Yuan, Dr. Exner, Rafi, and my colleague Ian from Oxford, and also Xiaolin, who did the animal experiment, Yan, who did the phantom experiments. And also, of course, my lab here, the Laboratory of Fields, Flows, and Interfaces. You know, I love them. I'm always just surprised at how good they are and how creative and energetic they are. So I want to really acknowledge every one of them for their creativity and the inspiration that they bring to me every day. And so that concludes my talk, and I'd be happy to answer any questions you have about this work.
I'd like to open the floor to questions from the audience. Are there questions? If there are, please go to the microphone if you can.
Thanks very much, Scott. Really interesting. So you do talk about your future applications. So can you talk about kind of the advantages of having, you know, basically nano bubbles to do things like targeted drug delivery as compared to what we do now, which is, I guess, is poly molecule?
Yeah, that's a great question. So, so I think my thoughts about the future applications of this are primarily based on discussions that I've had with other people. My expertise has so far been more on the manufacturing methods for the bubbles, and the applications primarily come from discussions that we have with actually clinician scientists at St. Mike's, right? So a couple of people I've talked to, for example, Darren, have suggested that if we can make different size bubbles, for example, they might extravasate to different parts and also extravasate only when there is inflammation, for example, only when there is disease, right, or only when there's leakage, right? So that's the aspect of being able to, not necessarily just because we can have nanobubbles, but because we can tune the size of the bubbles very precisely, right? So one example is, you know, in some inflammation cases, the leakage of the vessel are estimated to be, maybe 300 nanometers, right? So we can, for example, deliver a solution of nanobubbles bimodally. So half of them will be, say, 600 nanometers, half of them will be 100 nanometers. So we can functionalize the 100 nanometers bubbles with one kind of drug, the 600 nanometers bubbles with a different kind of drug. And so then they can localize in different regions based on their size and their drug. So we can deliver, I guess, with more precision. Yeah.
Go ahead.
Thanks, that's fantastic. I like the sequel to the movies. This was not a flop at all. So I appreciate that.
I didn't actually watch those movies. So I don't know.
You should. What I was going to tag along is Dr. Ori's question with regards to, all of a sudden start tagging these bubbles with agents or antibodies. How do you envision that the diffusion problem that you had as you transition from air to those carbons work out, given that you now have shells that are perhaps a bit heavier?
Yeah, that's a great question. Yeah, so what happens if you change the shell composition, right? So I can tell you, based on the literature, there's suggestions that changing the shell composition could change whether and how the gas phase diffuses into the liquid. But I can't confirm for sure, but I still believe that the dominant feature of whether the gas diffuses into the liquid will be the diffusion coefficient of the gas, right? In which case, I think it will be dominant over the effect of whatever you put on the shell, and hopefully that will be the case when we start putting drugs, when we functionalize the shell of the bubbles. Yeah, hopefully we'll see that the bubble shrinkage will not change too much. If our modeling is still correct, then that would be the case. Yeah.
Thanks.
Yeah.
Go ahead.
Really interesting to see all this. The model you used showed the shell was basically what we would think of as a lysophospholipid. So can you actually tell us what the shell is the first question, right? And then your pictures of the large bubbles look like multi-lamellar, not unilamellar structures, because a unilamellar structure would not be visible in that picture that you showed us.
Okay, so I'll answer the first question first. Yeah, so in our bubble lipid formulations, the shell is composed of a mixture of lipids and surfactants such as pluronic F68. Yep. No, so yeah, so to address the second question, so my understanding is that there should just be a single layer, although we haven't looked at this in detail.
It's not correct, because I've done lots of EM on these things, so that image wouldn't be a model here.
Which image are you referring to?
Your starting bubble.
The large bubbles, the micro.
The dark ring is much too large, and wouldn't see a long layer of that.
So these are, you mean the TM images or the bright field images that I showed?
Bright field, not the.
So the bright field, my understanding is that that's kind of like a refraction ring effect. We're not actually seeing that at the scale that you're talking about.
Basically, the structures you made, they're equivalent value. Nanometer is what we call a chylomicron.
I see. Okay.
Body-based chylomicrons, and they're 1,000 angstroms to 3,000 angstroms in diameter. Right. So that's the structure that you finally achieved. Right. Now, you take a look again, see what you've got, but I would say your largest structure probably is not unilamellar.
And what is the analytical technique that you would use to analyze the shell then?
Well, we start with EM, right, using different stains and such. And now we would go through maybe cryo-electron microscopy, this type of thing. So the techniques that I did have 30-some years ago.
Yeah, we should talk afterwards, but yeah, so in the large bubble case, right? So normally it's thought that it's a single layer of an amphiphilic molecule, yeah, because one side is hydrophobic, one side is hydrophilic. So if it's two layers, then both sides of that double layer will be the same polarity. Yeah.
So we typically get multi-lamellar structures with that first step.
I see. Yeah.
Right. So we
Okay.
So are there any further questions?
I think Daniel.
Any future directions to look at the pharmacokinetics of, for example, you see a nice image in the kidney with the monodispersive like nanobubbles, but is it due to because they are not being eliminated by the kidney, or it's just a contrast? So is there any component that is like just extracellular, or some of them getting into the cells?
Yeah, so that's a great question. Yeah, so I don't know if I can answer that properly. Yeah, so this is something that I think we would be discussing also with the collaborators on the clinical side. But right now, what we're thinking about is tailoring. I mean, one initial step is we're tailoring the size of the bubbles to intentionally have them extravasate versus not extravasate. And then using that tailoring of the size of the bubbles to figure out what is the pore size of, for example, the blood vessel when it's leaking. In terms of pharmacokinetics, yeah, so my understanding is that the kidney is able to clear these bubbles later on. But again, I'm not an expert in this, so I can't say it with a great degree of confidence.
Yeah, the only thing I would say is that one of the collaborators, Dr. Exner, I mean, she is doing the pharmacokinetic studies of at least the bulk nanobubbles, not the monodisperse microfluidic nanobubbles. I think there was one more question. Go ahead.
I was just wondering if you could comment on how you prepare your bubble samples for the electron microscopy. You're doing freezing.
Yeah, that's a great question. I can't quite remember the answer to that. Yeah, so the TM preparation, so we did this at SickKids. And there's a person there that's helping us with these TM images. I can't quite remember the exact, whether we had to freeze them or not. I think it might be freeze dried, but I can't remember for sure, yeah.
I think you use Scrapper, right?
I'm sorry?
Scrapper.
Yeah, I can't, yeah, it might be crowd TM, I'm not sure, yeah.
They were breaking apart in normal time. I was thinking much nano versions. And the normal time they were just running apart in the middle. I think we were using crowd there.
I see, yeah, maybe. I have to double check the notes, yeah.
Right?
Yeah, so if you freeze dry them, there must be a way that they don't actually shrink freeze drying itself.
Yeah, that's a great question. I'm not sure. Yeah, so I'm not sure exactly the protocol we use to make the TEM images, but we're interrogating the size of the nanobubbles using multiple methods. So TEM is one of them, right? And the measurements that we get using the bulk nanobubbles, using the TEM here at SickKids, is consistent with the measurements that they report in paper using the same approach to make the nanobubble. So I think that's a pretty good calibration of the approach that we're taking. And then we're also using the Malvern nanoparticle sizer to get the size distributions. And that's based on kind of a mass resonance effect. And that gives us the same range of size. So I think we're pretty confident in kind of the approximate size of the nanobubbles. Yeah.
So any other questions? If not, let's thank the speaker one more time.